let us look at some problems looking at, for example, specific heat. So, it says here it is desired to melt aluminium from a solid block at 15 degrees centigrade. The specific heats of solid and liquid aluminium are given and the latent heat is given. The density in the molten state is given and the final temperature is given and the melting point is given. We are asked to find out the mass of aluminium that can be melted if the rating of the furnace is 217 megawatts and its efficiency is 70%. So, we have over here let us say an aluminium block sitting inside some vessel in a furnace. This aluminium block is at 15 degrees centigrade. We start heating this aluminium block with a furnace which can give 217 megawatts of power. So, we heat this. What we expect is that the temperature of this aluminium will increase. At some point of time, it will reach its melting point, which is 660 degrees centigrade, and then it will start melting. So, while it is melting, the temperature does not change, but its volume changes, its state changes. It was initially solid, it becomes liquid, and then once all of it is molten, we are left with liquid aluminium at 660 degrees centigrade. And we are continuing to heat. So, once it is all liquid, its temperature starts to increase, and finally, we are left with liquid aluminium at 700 degrees centigrade. So, we are asked to find out how much of aluminium can be melted per hour. So, the process is in this fashion as we have just discussed. So, we can write down the formulae which are important. So, I am giving some amount of heat. The rate of heat transfer is 217 megawatts. So, what I can see is this heat would go into increasing the temperature of solid aluminium, melting the aluminium, and then increasing the temperature of liquid aluminium. So, I have Q dot is 217 megawatts. This process goes on for 1 hour. So, I can find out what is Q. One megawatt is 10 power 6 watts. So, this is the total amount of heat which is transferred. If I now look at the specific heats, I know the specific heats. So, what I can say is that in the case of a solid or a liquid, one of the things which we did not discuss, but we can easily see is that we had, for example, the heat transferred at constant pressure to be as m into Cp into delta T. Heat transfer at constant volume we had as m into Cv into delta T. The difference between Cp and Cv is the difference essentially between the enthalpy and the internal energy times something. So, what we can see is, for example, what we said is Cp is and we said that this is the relation. Now, in the case of a solid, what we see, or a liquid also for that matter, what we see is that the volume is very small because the density is very large. So, we can also write this as in this fashion. So, the specific volume for a solid or a liquid is very small. So, for example, if I was to take water, water has a density at say room temperature of close to 1000 kg per meter cube. So, the specific volume is about 0.001 meter cube per kg. So, what we see is that the specific volume is pretty small. So, this term is negligible. So, essentially for solids and liquids, what we see is that the enthalpy and the internal energy are approximately equal. So, because this is approximately equal, so this essentially means that Cp and Cv are also approximately equal. So, we usually just call it as some C, because it does not matter whether it is at constant pressure or constant volume, the values we get are essentially the same. So, we just call it as some C. So, we have here solid and liquid. So, what we can see is the heat transferred goes into changing the temperature of initially the solid. So, that is m into C into delta T. Then it goes into changing the phase from solid to liquid. So, in case of phase change, we talk of latent heat. So, in this case, we would talk of latent heat of melting. The latent heat of melting, if I have some amount of heat which I give, this would be m into the latent heat of melting. We will call this as something else a little later on. For the time being, I will call it as delta this is going from liquid, this is going from solid to liquid. I will call it as SF. We will look at other terminologies for this a little later on once we go on to the next topic, or maybe I will just call it as delta H and say it is, for the time being, maybe I will just say latent heat for the time being. I think that is going to be less of a confusion at this moment. So, it is given as this. So, while this process happens, there is no change in the temperature. All of the heat which we give goes into changing the energy of the substance or the enthalpy of the substance. There is no change in the temperature though. So, this is some m into latent heat, and then at this point, once this is added, if we add enough of this, all of the substance becomes liquid, and then whatever we add goes into, this is solid, then it goes into changing the temperature of the liquid. So, this is what we have. It is the same mass. So, we can take the mass out, which is essentially what we want to find. So, the mass is Q divided by all of this. So, I want to find out the mass. So, the heat transferred which I had is essentially 217 megawatts for 1 hour. I also need all of this other information. So, the initial temperature, so for the sort, okay, this is 317 in 10 power 6 into 3600. Now, the specific heat of the solid is 0.9 kilojoule per kg Kelvin, and for liquid it is 1.11. The latent heat is 390, the density in the molten state is 2400. What I have is that the temperature change here in the solid state, it goes from 15 degrees, which was initial temperature, to the melting point, which is 660. Then I have latent heat, and finally it goes from the melting point temperature, which is 660, to a temperature of 700 degrees centigrade. This is what it goes. What I am also given is that the efficiency is 70%. We will come back to that a little later on. So, I have an expression of this kind. So, I can find out the mass. These are all in kilojoules, and the top I have 317 in 10 power 6 into 3600 joules. Let me also convert that into kilojoules by multiplying by 10 power minus 3. So, I get the value as this. So, I can melt about 1120 tons of metal using this furnace, if all the heat which was given in this furnace was used for melting. What is given is that this efficiency of this furnace is only 70%. So, what it means is that I have a furnace, in the furnace I have an electrical coil to which I give this much of energy, but only 70% of that goes towards melting metal, the remaining is lost maybe as heat transfer to the surroundings. So, this was the ideal amount of mass which I could have melted if the efficiency was 100%. Because the efficiency is only 70%, the actual mass which I can melt is the efficiency times the ideal mass. So, that is 0.7 into this, which comes out to about 787 tons. So, in reality I can melt about this quantity of metal per hour in this furnace. So, that is what we see as this problem.